So the only two things that we have considered were parametric curves and functions of several variables. So any questions about these? So the idea then is to develop. It takes some time to develop the background for multidimensional calculus. But other than that, these two things will appear a lot, and in the meantime, the questions asked about them will be the same as in Calculus 1. So primarily is things such as certainly rate of change and the optimization possibly, and all of them are answered with derivatives as well as integrals. So differentiation is fairly transparent, especially for parametric curves. So not only you can do it once, you can actually you can keep going with this. You can go with the parametric curve on and on. So if you have a parametric curve, say P. Okay. Parametric curve made of two functions. Then you differentiate, and you can say it is made of its derivative is made of two derivatives of the two original functions. Then you can keep differentiating, right? There is really no problem whatsoever. And all of these have the same interpretations as in dimension 1, and that is the location versus velocity versus acceleration. But you can keep going, okay? In addition, you can reverse 2. You can reverse 2, and so from acceleration of force, you can find the velocity. From velocity, you can find the location, as long as you know the initial velocity and initial location. So that's all works out just fine. It fits perfectly into Calculus 1. Some of the questions cannot be answered, however, in the same manner, such as, for example, although the big deal in Calculus 1 about optimization and the maximum minimum points, well, there is no such thing. Right? If you think about it, so all we have is a curve on the plane, and well, there is no meaning of the. Well, let me make it clear like this. There is no idea of what is the meaning of the maximum or minimum point. Not in general. You can interpret them separately, x and y. And some of the question I think on the homework was, what is the say leftmost or right? This is the rightmost point on the graph. But that is. Did you have yeah?
Well, about the homework,
yeah.
Maybe I just haven't checked.
The current one?
Yeah, I looked last night. It wasn't up. Was it just put up today?
No,
Yeah,
no. I put is it there?
Yeah, it's there.
It was a bit
Yeah.
yesterday, but pretty late. So it's there.
Oh,
Okay. Yeah.
Is it not due till the 15th,
The
homework?
really, I guess I clicked on the wrong button.
Okay.
It should be Friday.
Okay.
So
as in tomorrow or next week?
tomorrow.
Okay.
Yeah, sorry about that. Yeah, I'll fix it. So, homework due Friday midnight. Okay, I'll fix it. Okay, so the rightmost. So do you recall the problem from last homework about rightmost point of parametric curve? Did you have a problem like that? Well, if you didn't, then it's certainly worth considering. How do you find the rightmost point of a curve, of a parametric curve? What is so special about this point?
it's the point where the x, or if f is our function that gives x values as a function of our parameter, that rightmost point is where f is maximized.
Yeah, that's right. So f at a maximum. Okay, and then everything applies as soon as we realize that, we don't need g anymore, and we visit entirely Calculus 1. Okay, the problem, that's how the problem is solved. Is certainly, even though it is still interesting once the problem is solved to go back and realize what the answer, not the answer like of two answers to, but rather the way you solve the problem. What does it tell us about parametric curves? It tells us something about the tangent line to this curve at that point, and it is vertical, right? So df prime, say a is equal to 0. That's what we're saying here. A not being that's log ft. Okay, so at this point you have a vertical tangent line. For a top point on the graph locally, even this one, the tangent line will be horizontal. Okay, so but other than that, there is no such thing as a maximum of a curve. I mean, if look at this curve, it does have a maximum or minimum. Okay, so problems like that would not be won't help. But the part we already have discussed about monotonicity of f and g, determined by the derivatives respectively, will tell us the direction of which the function goes. So, well, this matters which way. Okay, for example, if I take, say, this piece, what can I say about f and g here? F prime is positive as well as g prime is positive, right, at that location, because both x and y grow. If they are both growing, then both of the derivatives are positive. Okay, so one thing. Also, that is anti-differentiation, as I indicated, going backwards. The meaning of the definite integral is harder to explain. So if you start thinking about Riemann-Sonn's area under the graph, there is no area. There is no area. So if you try to integrate f and g, as I almost exactly what I just did, you're really not in the position to see any kind of areas under any kinds of graphs that you see in here, because those graphs will be on each of them will be on the, say, tx plane, and this is f, and this would be that definite integral. But it doesn't mean that there is nothing to talk about in terms of integration. In terms of integration, we'll be talking about length of curve. We're going to be talking about, say, maybe an object with to be in the form of a curve. We could find the central mass. The work. Okay, work performed by a force while an object is moving through some complicated curve. All of these will be integrals. Okay, so even though it is certainly more complicated than calculus 1, but it matches pretty well what we know. It is, however, very different with the functions of several variables. This is what we have on the right, or maybe this one. So let's see. Differentiation produces a function that is entirely different. It produces, as you can see, it is over there. It gives us a vector. So try to differentiate it one more time. What do we get? What's the meaning of the second derivative?
It's the change in the gradient.
What I meant to say is that we start with a function of two variables. Input is two numbers or location on the xy plane, xy. Okay, the output is a number. Okay, once we differentiate, the nature of that new function is very different from calculus 1, different from parametric curves, in the sense that this is still a function, but it's very different in nature from the original, because the input is still xy, but the output is a vector. A vector, remember, it's supposed to point in the direction of the fastest growth of the original function. So once you're outside of the realm of functions of two variables right away, and we barely were able to figure out the meaning of the first derivative, and it's already complicated. But if you try to differentiate this, you can try to guess what's going to happen. You will have to differentiate each of these, and each of which will produce a derivative, two derivatives. Okay, so altogether the number of derivatives becomes 4. So if you're looking for the second derivative of the original function, there will be 4 derivatives. There will be derivative differentiated with respect to x twice, y twice, and then xy and yx, depending on the order of operations, of the order of differentiation. So and we do need to differentiate twice, because remember, it has something to do with concavity. Okay, and that is clear. So that's, if I differentiate twice with respect to x, I will discover the concavity of this curve. Okay, if I do it with respect to y twice, I will discover this. What is the meaning if I differentiate with respect to y, then with respect to x? That remains to be seen. So in other words, things really become way more complicated right away. And then think about integration. So what is the meaning of integration of a function of two variables? Well, actually, anti-differentiation breaks down once again. So try to think about this function and try to, is it the gradient of some function of two variables? And that there is some subtle points that we'll have to deal with, even though it is possible to do, and we'll work it out, but there's some challenge. However, definite integration is very transparent. It is, well, you can guess what the meaning of, if I try to, what could be possibly the meaning of the integral of a function of two variables. Definite integral. So calculus 1, area under the graph. Okay? The graph is a curve on the plane, and the definite integral is the integral. Is the area. Okay, you can guess what the meaning is of a function that looks like this.
Is it the volume?
It is the volume under the graph, right? The volume under the graph. So if you want to compute volumes, or you want to compute mass, or momentum, or all of the center of mass, all of that will be the integration of functions of two variables. So something that you already saw a little bit in calculus 2, when you did volumes of revolution, for example, right? You got that? So that's a similar, but on a slightly more general level. Okay. So let me. I want to. The function that what I was just talking about, I want to show this one again. Where's my? My function of two variables. Here, no. Okay, sin. This is the one. This one. Okay, so it is just interesting to see more of it and look at that picture that I made. That it's not very. That on the right, the settle point is actually, this one has a settle point, except it is right here. That's a settle point. We just don't see it. So if I just move my window from right to left, okay, shift it. So if I put here -1, that should work. Okay, that's a settle point. So as you can see, the two different concavities meet together in the middle. So concave up if you go this way, and concave down if you go this way. Let me rotate it so you can see. Rotation. Okay. Okay. Well, maybe like this. Okay, so that's a settle point, or Pringle, or whatever, one of those, and you can see how these are actually two straight lines. Two straight lines meet together in the middle, and then there are four rather like wings. Two wings go down like this, and two go up like that, creating a settle. Okay, so that's what can happen. And incidentally. These are the partial derivatives. Okay. Well, anyway, let's continue on to spaces of multiple dimensions. Well, certainly, the fact that they have multiple dimensions does not exclude the possibility that the dimension is 1. So it will be that just the dimension will go from 1 and up. I put ... there because the big thing is visualization, and beyond dimension 3, the visualization is out. So why do we need multiple dimensions? Reason 1 is, of course, our physical space, the dimension of which is equal to 3, as far as we know. And then abstract spaces. not mathematic in the mathematical sense abstract, but they are made up to accommodate multiple quantities changing, multiple quantities to begin with. So any dimension, and just to illustrate what we did with the prices. Remember this. So this is time. This is wheat and what is sugar, and this is bread. Prices of bread. Okay. So as you can see, this is certainly dimension 1, dimension 1, dimension 1. Okay. Even with this, as we just saw, we plotted the function of two variables and the graph in dimension 3. Okay, the graph in dimension 3, meaning because there are 3 variables, so we already have 3-dimensional situations. Similarly, if you want to plot the graph of a parametric curve, not just the path, which is 2-dimensional, it will still be in dimension 3. Okay, but yes.
What bothers me about thinking about the graph of that is that we lose t. Would there ever be a case like that where we would arrive?
You're talking about this, right?
Yeah.
Yep.
I mean, would it ever make sense to, instead of considering a graph in R3 where we've lost t, to consider a graph in R4 where we include t? Was that?
Well, first of all, for this one, total it is 3. So because it's more manageable, it can be done with a pen until we have like holographic pen, and I can't wait until I can do this and draw something in the air. So we are looking at dimension 2, and then I can draw on a piece of paper or on the screen, and that's why we do not do the graph, we do the path. Okay, so path is 2-dimensional, the graph is 3-dimensional. But if we move to curves of like 3-dimensional curves, then to plot the graphs, they are 3-dimensional. The paths are 3-dimensional. Graphs are 4-dimensional. So how do you plot? There are tricks certainly to have extra dimensions visible, such as just not long time ago we did this, right? So dimension technically is 2. X and Y, but then using the color, we have extra dimension. Okay, similarly, you can have, imagine that you have a function of 3 variables. How do you visualize it? You visualize it like it's made of cells, little cubes, okay, and each of them has a number in it, indicating something. Maybe it could be prices, or it could be, for example, it could be temperature, pressure, density, whatever it could be. And once again, you can illustrate it with a color. Okay. There are other tricks. There might be, but this is the basic one, and we just do best we can. So we are trying to stick with these dimensions only in order to. So if we can make these 2 steps, then the rest of them can be kind of derived, and you are not going to do them with a pen anymore. So it will always have to happen inside your head. But the hope is that it's okay. It can be done. It can be done if you have a good idea of what dimension 3 feels like, not what it looks like, but it feels like. You can imagine all the algebra, as well as geometry, as well as calculus in dimensions beyond 3. Okay. So what is actually happens in real life if you were beyond these toy examples that I have here, you can have x1, x2, x3, x say 1,000. Instead of bread, what if it is a car? Okay, that's the price of a car, and it might depend on 1,000 different either commodities or spare parts and so on, and once again that part might still remain, so that you have every commodity or part depends on as a price depends on time, and then when you build a car from those pieces, including labor or whatever it takes, that becomes the price. So once again, double step, you have a parametric curve living in 1,000 dimensional space, and then you have a function, and then followed by a function with 1,000 variables. Okay, so imagining it, you don't want to start here because it's impossible to visualize. But little by little, we will see that it really doesn't matter if we just take the right point of view and we start thinking about the space not as a sequence of numbers, but rather we just say we can put like a large P here, just to remind us that this P is not no number, okay, but it is a location in 1,000 dimensional space. Okay, so if we do that, then we will see how we can do algebra, geometry, and calculus with these, in addition to those. So these are just numbers, so that's familiar. But this will have to be taken care of. Okay, so what is 1,000 dimensional space, if not just a sequence of these numbers? But that's only one way to look at it. Another way, and so in that sense, it is fairly predictable what we're going to do with it. We already did with this x, y, so a function of two variables, so we can certainly do differentiation with respect to each of these variables, and then that will give us an idea of what's going on in this whole thing. But there another way, that is we certainly should not overlook this. The physical space of dimension 3, which could be, who knows what its actual dimension is anyway. So physical space, and what's the problem with physical space in comparison to this? There are no coordinates. If I look around, I do not see any, I don't see this. So this is certainly familiar Cartesian system, which we're going to discuss now, but it is not exactly present in the physical space. So we have to construct it. Okay, so roughly that is our plan, is to develop the Cartesian system for dimension 1, 2, and 3 in a consecutive manner, and at the same time dealing with geometry first, then algebra, and then build on that calculus. Okay, so Cartesian system then starts with dimension 1. So dimension 1, meaning our space is a line like this. Well, in fact, there's nothing here. What I meant is dimension 1. Space is a line, but what line is not entirely clear. We can only do this, and there is nothing to indicate there is no origin, there are no units, and that's what needs to be built on top of this. So it's imagined like it is a road, and you certainly can. There is nothing wrong with the road if it does not have miles posts. Okay, but you can drive on it. But if you want to do some kind of measurements there, well, that's when you do need to introduce a Cartesian system of coordinates. Okay, so in fact, as we move on to dimension 2 in a second. And then what we're talking about, space is a plane, or looking like this. All Euclidean geometry is here without any help for Cartesian coordinates. Okay, so this is Euclidean literally what Euclid did, and whatever was happening until Descartes discovered or invented the Cartesian system. And you can do a lot. The Pythagorean theorem here, Euclid axioms, parallel and so on, all of these triangles, or whatever we know about triangles, sine law, cosine law, all of it is here, and it can exist without no need whatsoever for Cartesian system. Okay, so but that makes it very hard to do any kind of calculus. Okay, so if you have a space without any milestones or the ability to measure distances. Remember, we just did it. If you talk about the rate of change, for example, you got to be able to, you move from this point to that point, you got to be able to talk about that, about the change. What is the change? Like this. So we'll have to deal with vectors. But first just location. So what do we add to this? To this line, we add first we add the origin. That's number 1. Number 2, what do we add number 2? For the Cartesian system, one-dimensional Cartesian system.
We have to decide on a unit of measurement.
unit of measurement. So you could, let me put it this way. So unit. Okay, and that's well. There's one more thing. The origin, unit of measurement.
Positive and then negative.
Positive and negative. The positive direction. So the direction. Okay, so that's the Cartesian system. So the point, what is the point of the Cartesian system in that sense, is that something that is familiar is nothing but a point. Point on the line becomes something else. So it's the same point, but now our line is equipped with all this system. So what do we associate this point with? Say point P. Now what is it?
It's a real number.
That's right. So P corresponds to a real number. Every point on the line corresponds to a real number, and vice versa. Every real number corresponds to a point. And there is no ambiguity to every point corresponds to one number corresponds to one point. Okay? So how you can imagine how it happens. You take that unit of measurement and somehow manage to measure the distance from the origin towards that point, keeping in mind the correct direction. Okay, so in this particular case, you measure it. Maybe it looks like 3 units of measurements, roughly going from right to left, and it's in the opposite direction. So maybe in this particular case, P is equal to 3, possibly. Okay, so that is the idea. Now, if we move to dimension 2, the plan is similar. We have instead of a road, what do we have? So once again, to introduce the Cartesian system to the plane, what do we use? 2 roads. 2 roads, and it has a meaning in the sense that it is one-dimensional Cartesian system used twice. So that system that I have over there, origin, unit, direction, I use it twice. Okay, so 2 of those I have them here. In fact, let me emphasize that point for a second. If I can just if I just I do twice to begin with. So I'll have one line, Cartesian line, if you like, Cartesian line, the other Cartesian line. And then I will add the exact same thing to both of them, and I will add then origin. And I will add the unit. Well, as you can see, I'm trying to emphasize that there's really no particular way. These are unrelated so far to each other. Okay, so the second one I use the unit. Okay, so the unit could be just the same as before, or it could be smaller. I mean, they could be different units. So we considered prices, but so prices, presumably they're both measured in the same unit, $1, for example, but you can imagine that you have a space, and then you can have horizontally, vertically, totally different units. You can, for example, you can have one measured in dollars and the other price is measured in pounds. Okay. Also, remember you did this so many times in calculus 1. Then you have one axis is for, say, time, measures in seconds, and the second one is measured is location for distances. So it's measured in feet, for example. So these don't have to necessarily have anything to do with each other, unless we're doing a particular 2-dimensional physical space. Okay, well, that is my two axes. To distinguish, I have to name them, and I naturally call them as we have, x and y. And then I finally put them together. Okay, what's going on here? Oh, okay. And then I put them together as if 2 roads. I put them now as Descartes did in a 90 degrees way. it is very accepted in mathematics to put the two origins in the same point when we cross them. But actually, if you use, for example, Excel, or maybe here, it's not necessarily the case. So you could actually, it has options when you plot the axis. You can put any axis wherever you want. You can have the origin here totally unrelated to the origin there. Okay, so it is possible. Let me just make that quick point that it is possible to combine them like this. So since they're perpendicular, they have to intersect, but the origin might be like this. Okay, so this is say 1, 2, 3, and I'm sorry, 0, 1, 2, and this is 0, 1, 2 in that direction. So it is possible. There is really nothing wrong with that. But the assumption in mathematics is this. Okay, so then there are units, and this time I'll put them like this, like here. This will be 1, and this will be 1, and this is x, and this is x, and this is y. Okay, so we put them together. Now what? Once again, I didn't say what I did. I didn't explain everything that I did. I took these. Okay, so that is more or less clear. I put them in such a way that the origins, origins come together. What is the another subtle thing that I didn't mention?
They're
Degrees. What?
orthogonal.
Oh, okay, I just did it. Okay, there is more. The 90 degrees is kind of ambiguous. I could have put a y arrow down, for example, right? So once again, in the assumption, it's not 90 degrees, but 90 degrees measured from x to y, from the positive direction of x to the positive direction of y, from positive x to positive y. Okay, so that's another assumption. And even though you certainly can imagine this thing being upside down, it is just not the way it's done. And if you try to explain it to somebody, you'd rather be on the same page. Okay, so similarly, we certainly can. Well, now you see the transition from dimension 1 to dimension 2 has been accomplished. Well, I'm sorry. Let's do that idea. That idea we can repeat exactly. That idea over here. We can, the idea is here, the point of the whole thing is here, that points correspond to real numbers and vice versa. Here it is different, so the point is points, the Euclidean points right here on that plane, pure blank piece of paper, we have points there, and points correspond to, well, let's say a point corresponds to what? A point corresponds to a pair. The difference between two real numbers and a pair of real numbers is that order matters. Such as x1. Okay, so if my point is here somewhere, you know how it is done. You measure, roughly speaking, the distance to the x-axis. That will be the y-coordinate, and you measure the distance to the x-axis, to the y-axis, that will be the x-coordinate, okay? And never forget the other part, and vice versa. Every point corresponds to a pair of real numbers. Every pair of real numbers corresponds to a point. The correspondence is unambiguous, one-to-one, and reversible. Okay, so if you go this way from points to real numbers and then go back from real numbers to points, you arrive to the same location, right? Okay, so and then we made this transition twice we did the Cartesian coordinates twice, and the similarity or analogy, parallel development is already becomes to be visible. Dimension 1, dimension 2. The x's, the coordinates, the algebra the geometric entities points are represented by, say, numerical quantities such as either a single number or a pair of real numbers, and then you can already guess what's going to happen in dimension 3, right? So dimension 3. Let's do dimension 3. So what about dimension 3, which I'm not going to try to visualize. Well, let's say this is dimension 3, so what do we do?
We just do the same table, and we have one more one more axis to.
One more axis. So so once again, the points in the physical space. And so that's without good explanation what it is, but instead trying to understand this this physical space by means of the Cartesian system. So suppose the Cartesian system already is given, and it will be indeed 3 axes. So that starts with just the same way with nothing but 3 axes. Well, you don't have to say axes. You can call them lines. So real lines. Real lines, what is an axis? It is a real line that is equipped with the Cartesian system. Okay, so I start with the 3 lines, but then I continue on by giving them all directions, giving them all origins, and giving them all the unit. Once again, they could be the same, they could be different. I put the same. If you really want to talk about the physical space, then certainly you don't. Well, actually, it does happen. It actually does happen when different in the physical space, your location is given in terms of 3 numbers, but they are measured in different units. Does it sound familiar? No? A plane. The distance will be in miles, but the altitude will be in feet. Okay, so weird, right? But considering that's the space of entirely, it is uniform in any direction, not only vertical and horizontal, but any direction you go, it looks exactly the same. It's not uniform. It's the word is I think homogeneous, maybe. So all no, it's what is the word? That is all directions are equal. Isotropic, maybe. Well, anyway, so all directions are different, and yet you could have, once again, distance or x and y coordinates. So you have a map, and you see where your plane is going. The horizontal coordinates x, y are so x, y are in miles. In the meantime, z is in feet, maybe 1,000 feet. Still different units. So it's possible to have different units. Doesn't matter. We'll put these together. We could handle all of them. We put them all together. Once again, the requirements are similar. So what are the requirements? They're same origin. Okay, same origin, 90 degrees between all of them. Between any pair of axes. So there are 3 axes, so there are 3 pairs. So these are the 90 degrees appears 3 times. Same axis, 90 degrees between any pair of axes. But we already know that the second statement has to be done more carefully, and so then you have to be clear about how you actually measure those angles, and you measure them not like this, like in the Euclidean sense or high school geometry sense, but you have to measure in the right direction. So directions of angles matter. I'm not sure you've seen this in Calculus 1 or 2. Measuring not rather angles, but rather measuring not the angles of triangles. We're talking about the angles of rotations. Okay, so this is x, this is y, this is z. Okay, the rotations are measured from x to y, from y to z, from z to x. So these are all rotations. And when you rotate, it certainly matters which you're looking at the end of my axis, or I'm looking at the beginning, the positive half of my axis where the arrow is. So the rotations are from positive to positive. So let me show you. So this is 1 from x to y, 90 degrees, right? And then this is the other one, 90 degrees. And then finally from x to z, 90 degrees. Oops. Okay, so it's still, by the way, it's still ambiguous. So you have to remember this. Either it is a three-finger rule, or it is the rule of, not rule of thumb, but rather what's it called, right handle?
Yeah, right hand.
Right handle, or how the screwdriver works. I'm turning my screwdriver from x to y, and my screwdriver is moving in the z direction. Okay, so that is the actually, so the screwdriver idea. So then everything is unambiguous, and we have also, and one more thing is the units. Okay, so points, a point corresponds to a triple of real numbers, and vice versa. Dimension 4. The only trouble with dimension 4 will be that we won't have a picture. But otherwise, you can imagine that everything is very similar. So you have 4 axes. They have the same origin. There are 90 degrees between them. The rule of 3 will be more complicated with the rule of the screwdriver, or rule of right-hand rule. That's another way to where your finger's going like this, okay, and your thumb is going up. So that's the rule of. It's not the rule of thumb, but I think it's the right-hand rule, what it's called. So your fingers are moving from the x-axis to the y-axis like this, okay, and then your thumb is pointing in the z direction. Okay, so that would be harder to explain in dimension 4, but it still can be done. We don't have to worry about that necessarily. In dimension 4 and higher will be handled primarily algebraically. Okay, so it will be simply x1, x2, x3, and x4. I want you just to notice that x, y, z kind of will be fading away, because we know that it could be, the dimension could be 4, it could be 34 or 54. Or 104, and which means that we will run out of letters of the alphabet. And not only that, the bigger problem with using different letters is that you won't see the symmetry of things. So because they behave identically, they play an identical role within the system, and so just giving them different letters will eventually be seen as a confusing feature. So we'll try to avoid that. But the main thing is still, we're talking about points. And we want to say point, even though in the back of our mind, it will be that it is a triple of numbers. But first of all, it is actually really a point. Calling it a point easier because, well, you don't have to think about coordinates. The most important thing is that, especially in the physical space, the coordinate system might vary. Okay, not only you can put origin in a different place, you can put the axis in different directions, you can have different units, all of that is possible. You can just rotate. Imagine that you rotate, you have, certainly when you are in a room, you can look at that, the corner, and you can see like you have 3 axes here, right? And vertical, horizontal, 2 horizontal, 1 vertical, but you can pick any of the other corners and they will be just as good coordinate systems. So that is why we want to have a system that is independent of any particular choice of coordinates. Okay, so moving on to geometry. Okay, so we want to do, this is Euclidean geometry. It is a hard way of dealing with things when you don't have coordinates available, but now we do. So we want to be able to handle the same problems, the same issues, but using the coordinates. What's the number 1 issue in geometry? Distance. So there we go. So in all of these 3 and even 4 dimensions, we want to be able to compute distance between 2 points by means of their coordinates. Okay, so that's the geometry that we care about. So geometry. So number one issue, given 2 points, P and Q, what's the distance? Okay, so specifically we want to answer in terms of the coordinates of P and Q. So in other words, we assume that the not only the problem stand itself stands independent. So 2 points, you plot from point here, point there, you want to know the distance. You have a measuring stick, you can answer the question. But now we assume that the Cartesian system is fixed. The Cartesian system is provided, and which means that we could simply, the coordinates are also provided for each of points P and Q, and we want to know the answer. So let's just answer the question. So P and Q, what's the distance between P and Q? In dimension 1, P and Q are actually numbers, so what's the distance?
The absolute value?
Yeah. Well, absolute value of what?
Oh, of the difference.
Of the difference, right? P and Q. So P and Q are, in a sense, their own coordinates. So we just write absolute value, P minus Q. Okay, that gives us the idea of that we will recycle this formula, dimension 2, 3, and 4, because it will give us, this is happening within the x-axis. The same thing will happen within the y-axis. Knowing the distances on the axis, we will find the distance which is diagonal. Okay, so we'll just do it next time. Okay.